manage to solve general value problems.
I stole the thing. No, it's not mine.
All right, good morning, everybody. I'm Craig Shearston from the University of Alberta. I'm a member of the Reinforcement Learning and AI group led by Richard Sutton. And today I'll talk to you about some ideas I have on introspective agents, confidence measures for general value functions. So to give you a bit of context here, a little bit of setting, I'm interested in continual learning in the real world. So the world is a big, complex, messy place, and our resources are always going to be limited. We need approximations and we need good enough solutions. And so goal-seeking agents or robots living in this world like this, I believe they must be able to learn about the world all on their own. And that their understanding should be grounded in their own experience and sensory motor stream and not dependent on external supervisors or programmers. So I think a lot of us in the room probably are on the same page with that. So one way of representing knowledge that I'm going to be kind of framing this discussion in is this idea of predictive knowledge, which I'm defining as a collection of temporally extended or multi-step predictions about observable outcomes. So we're talking about predictions that go off potentially far into the future, not single-step predictions as is often talked about in the machine learning community. Now, introspection is this idea of examining one's own internal mental processes. And so this kind of leads me to point one here, is that I'm going to argue that rather than just looking at the external world as being interesting, we should also be looking at the internal world. And the internally generated signals might serve as part of our representation, and they might serve as targets for prediction or targets to be modeled. And then my second point is going to be that many of these internal measures seem to appear to do something like confidence. And rather than taking a single view on confidence, that we can ask lots of different questions about our data, take lots of different views on this, and then ultimately I believe this will allow agents to make more informed decisions about how they improve their knowledge and how they gather knowledge, and ultimately make better decisions about how they interact with the world. So this leads me to the general value function. This is an extension or a generalization of the value function methods used in reinforcement learning. But instead of predicting cumulative reward, now we're looking at any other measurable signal. And the GVFs allow us to kind of semantically specify questions about temporally extended behavior of measurable signals in expectation. And we have three parts. One is the policy, or the way of behaving that we're interested in, the cumulant, which is our prediction target, and then our prediction timescale. The nice thing with GVFs is they can be learned directly from observation without the need for a supervisor. So let's take one little example here. We've got this little mobile robot that's great here, and we can ask this question: how much current will my motors draw over the next 3 seconds if I spin counterclockwise? So we've got kind of the three components there. We've got this prediction target, the current. We've got our prediction time scale, 3 seconds, and then we've got this policy, spinning counterclockwise. It's a very simple example. And so if GVFs specify the question, we can use temporal difference algorithms to start to answer those questions. And TD methods, taken from reinforcement learning again, have some really nice properties for acting in the real world. They're online, they support incremental learning, often strictly incremental learning. Function approximation, they bootstrap, just lets us learn reasonably fast. They learn directly from observation. They're policy conditional, and when we use them with linear function approximation, they have a linear computational complexity. So some very nice characteristics for operating in the real world. So most of the work that's been done with general value functions has focused on predicting or modeling external signals. And so this is kind of the first point of this talk, is that we should also be looking at internal signals. This might include the output of the general value functions themselves, so the predictions that we're making internally. These might include the prediction errors, such as the TD error, temporal difference error, or other parameters that are generated as part of our learning process and algorithms, such as step size and weight changes and these kind of things. But the point at the end of the day that I'm making here is that all signals are data. Internal signals are simply another source in the data stream. So then the question comes up, well, what do we do with these signals? Well, we model them. That's one of the things we do. We can ask questions about them, predictive questions. So whether they're internal or external, we can use those as part of, as prediction targets. And we can also use them as part of our answers. These signals, again, external or internal, can serve as part of our feature representations to learn other things. And maybe in some special cases, we might use these signals to modulate other processes that are going on internally. So if we look at a pretty standard scenario, we have sensory signals coming in on the one side. We convert that to some representation from which we learn a value function and ultimately a control policy or a way to behave in the world that allows us to maximize a goal or maximize the reward that we get. So to put some of these ideas in context of using internal measures, we have this predictive representation of state. This is one possible architecture you might take, where you can have a number of general value functions predicting all sorts of things about the world. And then we use those predictions of the output to produce more further representation. And then you can produce more predictions out of this. So the idea here is that we build layers upon layers of predictions. And we believe that this will allow us to represent more and more abstract concepts. Now, another way to think another architecture we could look at is these temporal difference networks. So basically here what you have is the prediction of one general value function is being used as a target of another general value function. So we're essentially trying to make predictions of predictions of predictions. This is something that's already in the literature, these kind of ideas. So we have these internal measures, and as I kind of alluded to at the beginning, some of these I think we can kind of interpret as confidence measures. And I'm using the term confidence here in kind of a loose way. I'm defining it as the level of trust that we place in a signal or a prediction. This allows me to kind of encompass maybe some of the statistical approaches to confidence, as well as maybe some more subjective approaches. But what you'll typically find with approaches to confidence is a single number. In the example I'm going to show you in a little bit, I'm going to be predicting a hue or a representation of color. And so it might give us a prediction of, say, 130 plus minus 10 or 60% certainty or something like that. And having that single kind of compressed number, that's really useful. That can be useful for knowing, say, when to act or not on these predictions, or useful for acting cautiously. It might also be useful for exploration. So you can imagine in a world where you're expecting it to be, or where you're thinking it's a dangerous world, you might want to stick to things that you have really high confidence about and avoid low confidence scenarios. Whereas if the world's really safe, then low confidence states are opportunities to explore and learn more about your world. But an agent might want to do better than this. It might want to know where its sources of uncertainty are coming from and ultimately how it can improve its knowledge and its predictive capabilities. So this leads me to my second point, which is that rather than taking a single view, compressed view on confidence, we can ask all sorts of questions about our data, lots of different views on the data, and then ultimately I believe that this will allow an agent to make more intelligent, more directed actions to improve its knowledge and ultimately improve its predictions and its ability to behave. So we might ask questions like, how far into the future are we predicting? A prediction 1 minute into the future might be much more certain than a prediction, say, a year into the future. Or how long has it been since this state was visited? Maybe I've had really good prediction success, really low error in this particular state, but it's been a year since I visited this state, and so I might want to be a little hesitant about trusting that. So So we'll look at a quick example. We've got this little robot in a 3x3 grid world. We've got 4 actions, up, down, left, right. And his observations are the color of the wall, this hue here. And hue is a real valued number between 0 and 360. So it's a real valued prediction he's going to make. And he only gets to observe the wall when he actually smacks into it, so he doesn't know it from a distance. Now, to explain the diagram a little bit here, we've got these cells, and they have these funnels opening in the direction of prediction. So in this particular one, orange means that if we went all the way to the left, we'd expect to see orange. In this case, that's right. And here we'd say, well, if I went all the way to the right, I'd expect to see this green color. And we can see that that's not correct. So this example, the robot's going to move randomly with a preference for moving up and left, and I've used tabular features. Further, the hue of the wall may change at each time step, so there has some variance about a mean. The top wall has high variance, and the bottom left wall, the cyan, has low variance, and all other walls here have no variance. So let's just add one source of information, one additional source of information into the data here, one look. I'm calling familiarity. This is like visitation. By far, this is the most common approach that I've seen in the robotics literature that I've read so far. But basically, counting experience. Black is going to indicate low familiarity. White indicates high. And we can see right away that this robot has only explored the upper left portion of the world. So if that was all you had, then you might be tempted to trust those predictions. But as I showed you on the previous slide, we already know that some of those are wrong. We as the outside observer. So let's add another view into our data. Here now I'm using the squared temporal difference error. So that's our prediction error coming from our TD algorithm, taking that and squaring that, and then I'm using that as a prediction target for one of our GBFs. So basically we're predicting error. And this turns out to be related to the variance of the return. Black again indicates a prediction of high error, and white indicates a prediction of low error. And I've initialized as high error. So we can see from this that actually, despite having we've got lots of experience up here, we only have low error really as we move leftward. And if you recall from previously, I said that this green wall has very high variance, and this orange wall has no variance. So that's kind of showing up here. So just by taking a few additional views on our data, we've already been able to kind of suss out some of the causes for uncertainty and provide, I think, more actionable metrics for the robot. And I expect that, as we took more views on the data, that this would improve that decision-making ability. So just about wrapping up here, introspection. How would we actually use this? Well, we can imagine using it for planning or moment-by-moment decision-making. We can ask questions like, well, what action will take me to states I've never seen before, or to states with low variance, or with low prediction error, or where I just haven't finished learning? And one example I like to give is this idea of cutting a tomato. So you can imagine that if you have some sort of measure on the position of a tomato, you might want to know, well, what policies, what ways of behaving would produce low variance? What are policies do I predict would produce low variance in this tomato's position while I cut it? Maybe that's just grabbing the tomato with your other hand. So in conclusion, kind of two main points here are that we should be looking at internal signals, not just external signals. We should be modeling those, using them as prediction targets, as well as part of our representation for producing other predictions. Some of these measures look like confidence measures, or seem to be related to sources of uncertainty in our prediction. And we should take, this is kind of one of the big points, is that we should be taking lots of different views on our data, and ultimately that this will allow us to produce an agent to make better decisions about how it acquires knowledge, improves its predictions, and ultimately its ability to act in the world. All right, thank you very much.